transmitiendo por nuestro canal de YouTube. Hola, pues bienvenidos al Instituto de Ciencias Nucleares. Les damos la más cordial bienvenida a nuestro workshop Materia Cuántica Topológica, Fundamentos y Aplicaciones. Para dar inicio a este evento, saludo con mucho gusto al doctor Alfred Uren Cortés, director del Instituto de Ciencias Nucleares. También saludo al doctor Luis Fernando Urrutia Ríos, investigador del Departamento de Física de Altas Energías del Instituto de Ciencias Nucleares. Asimismo, al doctor José Alberto Martín Ruiz, investigador del Departamento de Estructura de la Materia, también del ICN. Y al doctor José Eduardo Barrios Vargas, investigador de la Facultad de Química de la UNAM. Le cedo la palabra al doctor Luis Urrutia, quien a nombre del comité organizador nos dará unas palabras.
Bueno, ¿se escucha? Sí, bueno. Good morning, everybody. On behalf of myself and the organizing committee members, Dr. Eduardo Barrios and Alberto Martín Ruiz, we extend you a warm welcome to the second workshop on topological quantum matter. I will say a few introductory words to set the stage of this colloquium. Well, the study of topological matter presents at least two broad relevant aspects. On one hand, it is of natural interest in condensed matter, where the aim is to establish theories to explain their properties and also to develop experimental applications which might lead to technological advance involving new materials. On the other hand, topological matter provides an excellent opportunity to test and even to extend many concepts and ideas of high-energy physics, such, for example, as new quasi-particle excitations, anomalies, gravitational theories, violation of space-time symmetries, just to name a few. In other words, many very constrained and prohibited realizations in high-energy physics might become perfectly physical in this sector of condensed matter. In these ways, the emergence of topological materials provides an ideal opportunity for the cross-fertilization of ideas between these areas. The emergence of topology in condensed matter can be traced back to the discovery of the integer quantum Hall effect and to the subsequent identification of the corresponding Hall conductivity in terms of a Chern number, which is a topological invariant. Later, the importance of these new properties for classifying phases of matter was endorsed by the 2016 Nobel Prize in Physics for Thales, Haldane, and Kosterlitz. Among the most well-known and first discovered topological materials, we find graphene, topological insulator and superconductors, and wild semimetals. Nevertheless, recently, the possibility of finding new topological materials has grown notably due to a method proposed by Bernevik, Felser, and Weidenkopf, which allows predicting their existence by analyzing the symmetries of the crystal structure. Applying this concept, approximately 27,000 samples were investigated, and around 27% of them turn out to have topological properties. Later studies allow to estimate that around 53% of all existing materials have topological properties around the Fermi level. This fact has greater relevance due to the possible impact of topological phase on technological applications in areas like nanotechnology, spintronics, quantum computing, just to name a few. A comment in Nature Research highlight on the occasion of the 15th anniversary of topological insulator in 2023 remarked that perhaps in another 15 years, the physics of topological material will produce practical application. In relation to this timing, and for the impatient executive of our funding agencies, it is worth recalling the anecdote attributed to Rudolf Hertz. To recall, he demonstrated experimentally the existence of electromagnetic waves in 1887, as predicted by Maxwell in 1864, and without which our current society would be unimaginable. When asked about what practical applications he foresaw for his discovery, he replied, none, I did it just to prove that Professor Maxwell was correct. Okay. This meeting is hosted by the Instituto de Ciencias Nucleares at Universidad Nacional Autónoma de México, and it is organized by a collaboration between colleagues at the Instituto and the Facultad de Química de la UNAM, with the support of CONACYT, which is our local funding agency. We extend our sincere appreciation for the support to the following interns. First, to the director of the Institute, then to the administrative secretariat, particularly for the logistical support provided by the staff, to the computing unit for providing the technical facilities for the development of the event, to the science outreach unit for promoting the event through various social media channels. Last but not least, our warmest gratitude to the distinguished speaker who will be participating in the workshop, as well as to the general audience that is present here. It is now our pleasure to invite the director of the Institute, Dr. Alfred Uren, to deliver an inaugural address and officially launch the event. So.
Good morning, everyone. It is a real pleasure for me to welcome you all to our institute. And I'd like to just say a few words. The United Nations has designated 2025 as the International Year of Quantum Science and Technology, marking a century since the birth of quantum mechanics and highlighting its transformative impact. Our understanding of quantum effects has already led to groundbreaking applications that have profoundly influenced today's digital society. These include smartphones, computers, lasers, and advanced medical diagnostics, all of which are based on exploiting the quantum mechanical properties of matter. A new quantum revolution is now underway, driving breakthroughs by harnessing quantum phenomena such as superposition and entanglement for innovative applications. These emerging technologies are collectively referred to as quantum technology. Imagine a world where technologies are inherently protected against disorder and impurities. This is the promise of topological quantum matter. In the early 1960s, George Gamow made a notable observation in his renowned biography of physics, suggesting that number theory and topology were the only purely mathematical disciplines without applications in physics. Today, the applications of topology in physics are vast and profound. Topology, a branch of mathematics concerned with properties that remain unchanged under continuous deformations, plays a crucial role in understanding the emergent topological phases of matter. These phases are determined not by the topology of the material samples, but by the topology of the bands in the energy spectrum. Such materials form a vital link between high-energy physics and condensed matter physics, as the quasi-particles within them are governed by the same principles as elementary particles. The workshop Topological Quantum Matter, Foundations and Applications 2025 aims to bring together experts across various facets of topological quantum matter, highlighting the synergy between condensed matter and high-energy physics. This event also seeks to foster research in Mexico and encourage further international collaborations. The inaugural online edition in 2022 attracted over 200 experts worldwide, discussing the latest advancements in the field. This year's in-person edition will host over 100 participants from various countries. The conference will cover a wide array of topics, from topological insulators to topological superconductors, offering perspectives from both high-energy and condensed matter physics. With that, once again, I would like to welcome you all, and I declare this event inaugurated. Thank you.
We started with the first talk in the morning by Professor Fratkin. Let me give a brief introduction of his career. He got a bachelor degree of physics in Universidad de Buenos Aires, Argentina, UBA. He got the PhD physics in Stanford University, California. After took postdoctoral positions at the University of Illinois in Urbana, and became member of the faculty of the Department of Physics of University of Illinois since 1981. Later, he was named Donald Bigger Professor of Physics at the same university, Illinois, since 2015. And recently is the director of the Anthony Leggett Institute for Condensed Matter Physics since 2011. He's member of the National Academy of Science of the United States since 2013, and member of the Academia de Ciencias of Argentina since 2019. Professor Fratkin, which is very well known for his many books, works in the area of quantum field theory and condensed matter physics, and made many contributions to lattice gauge theories, disorder system, fractional quantum Hall fluids, and topological phases of matter, and high temperature superconductor. It is my pleasure to introduce Professor Fratkin to you.
Yo organizo un seminario, así que no se hace esto. ¿Está bien así? Ok. Voy a cerrar esto yo. Ahí tengo ya tengo acá. I assume, if you want, I can give the talk in Spanish, but I'm not sure if it doesn't matter to me. Okay, we'll do it in English. If people have objections, I can turn to Spanish, or Castellano, as we say in Argentina. Okay, it's really an honor to be here. This is the first time I come to UNAM. The only other time I've been to Mexico proper, I've been close I've been to Baja once, but to Mexico proper, I would say, only more than 20 years ago, I went to Puebla. But, for actually a similar type of meeting, so it's a real pleasure to be here. So since this was a lecture, I decided that instead of using slides, I was going to use my iPad and write, as I got used to do during the pandemic. So that's why it's all handwritten. So my handwriting is not excellent, but and on the iPad I still have problems, so you can see that it's a little fuzzy. But okay, so let me tell you what the talk will be about. So what are topological phases of matter? In some sense, these are the most boring states you can imagine, because unlike other states of matter, if you look in the actual material, in the actual physical system, there is nothing that you can detect locally, okay, except for possibly edge states, okay? So these are phases that don't have any broken symmetry for the most part. In some cases, they can coexist with a broken symmetry, but this is sort of incidental. Okay, so there are two types of these phases that normally are discussed. So in this sense of what is topological here, there are two types of topology that are actually involved here. One is already was mentioned by the director of the ICN, is the topology associated with the properties of the band structures of the system. So these are mostly non-interacting systems, or as we normally call them, one-electron systems. They are weakly coupled. Because of that, they are not in the strong coupling regime. And the topology is hidden in the properties of the quantum states associated with the advance to the electronic structures. Okay? This is a problem that should have been solved at least in the 1960s. Okay? At least. And in fact, the seeds of these ideas were already present then, but people thought that the electronic structure was understood by Bloch in 1929, I think, in the very early days of quantum mechanics, and the only thing they had to do was to turn the crank and use the computer to figure out what the band structures were. And there was an implicit assumption that, as you will see, will play a role here, that, you know, in the Bloch states are the states of particles of electrons, say, in a periodic potential. And so they are classified in terms of what are called Brillouin zones. So they are bands, and the momentum states, or quasi-momentum more properly, actually only take place in a Brillouin zone, which is actually a torus because of periodic boundary conditions. And the fact that this was a torus was not viewed as important. And there was an implicit assumption that the states, the one-particle states, the Bloch states, are globally well-defined on the Brillouin zone. In fact, this question was never formulated until 1982 by Thouless, Komoto, Nightingale, and Denise, who were studying the problem of electrons in a magnetic field on a lattice. So they were motivated by the integer Hall effect in that case. And then they found that, in fact, that the band structures of those systems actually have interesting topological properties, and they are classified by topological quantum numbers. Okay? So I will discuss some of this in some detail. Systems of that type, which for the most part, I mean, they don't break any symmetry, they are in that sense rather boring, but they have the property that usually they have symmetry-protected edge states. And much of what you know about the systems come from the existence of these edge states. They also have some so-called generalized symmetries, which probably will not have time to cover, but maybe I will discuss some of that at the end of tomorrow's lecture. There is another class that in some sense is more profound. So those are called symmetry-protected topological phases of matter. The symmetry plays a role. For instance, in the quantum Hall effect, the symmetry is a U1 symmetry associated with charge conservation. Okay? And in other cases, there could be some ZN symmetry or some other symmetries associated with the band structure itself. But for the most part, is some form of charge conservation, which is a continuous symmetry, in which case the edge states actually carry some charge. So in the case, the so-called topological order phases, sometimes called enhanced. I never liked that title, so I don't use it. People use it more broadly. But they're more properly defined as topologically ordered phases. Again, these are phases which are rather interesting. They don't have any local order parameters associated with them. You cannot investigate their properties by coupling to some local operator. Okay? The operators associated with them are non-local. And people with a high energy background probably are familiar with them. These are things called Wilson loops. The Wilson loops, roughly speaking, describe the word lines of some heavy particles, quasi-particles. And in most of these examples, the particles have unusual quantum numbers. They carry fractional charge, for instance, and more interestingly, they carry fractional statistics. In other words, they are not fermions or bosons. That's where the term anyon or any-on comes from, and they are generalizations of this idea. I always try to find a good way to it's impossible to translate this type of words into different languages since they don't have a meaning in any language. Okay, I think, for instance, Feynman unfortunately visited Mexico many years ago. He died many years ago, but even earlier. and decided to call the quarks quarkos, which is offensive. What can I say? And I still see in some texts using the term quarkos with C, of course. Of course, quark doesn't mean anything in English either. It's something that the Germans eat for breakfast, I think. Okay, so it doesn't really mean. I don't know why it's called quark, because German like that word. The same is true with anyons. I try to find for he's a famous professor in Argentina. I think he came many times to Mexico. He died years ago, Jose Jambiagi. And he liked, he's one of the inventors of dimensional regularization. So he liked to, dimensionally continued things. I need to find, to write a paper for him, in honor of him. So I call them cualquierones, okay? Which is equally offensive, and I only used it once, okay, I have to say. Okay, I will not use that term, fortunately it will be in English. And when I say anyons, you talk to a chemist and they think it's the opposite of a cation, but it's not, nothing to do with any anions, okay? So they carry fractional statistics, so they are generalizations of the quantum statistics that we are used to. And quantum statistics is based on the non-interacting picture because you construct the Fock states as product states, essentially. And these are things that cannot happen in states of that type. So inherently they involve strongly coupled systems. And it turns out that some famous problems or systems that use or studied in lattice gauge theory, for instance, the so-called deconfined phase of discrete gauge theories, for instance, they are actually topological. They are the simplest example. And they were rediscovered by Kitaev and gave them the name the toric code. Okay, for me, it was just a Z2 gauge theory when I was a kid. Okay, but it's the same problem. Okay, so these are. So I'm going to first discuss examples of so-called SPT phases, or symmetry-protected topological phases of matter. Actually, I'm going to change the order already from this. Later, I will talk about topological order phases. But I will start with the discussion of what is a quantum anomaly, since it plays a role which is important for this. And for people in higher energy physics, probably, since there are some of you in the audience, you probably are more familiar with the concept of anomalies, and this is actually a good realization of that. I don't think I will get to talk about generalized global symmetries. I am like a good politician. I always promise more than I ever intend to do, if anything. Okay. Okay, let me begin with something we understand, which is not a topological phase of matter. These are the so-called conventionally ordered phases of matter. Okay, so we understand these problems quite well. There are many examples. I know magnets, superfluids, etc. That inspired many other ideas, like the Higgs, and all of that essentially has this as an origin. And I hope I didn't offend anybody by saying that, but it's the truth. Okay. So typically, these are systems that have some global symmetry, which may be continuous or discrete. In the case of a magnet, for instance, if it has a uniaxial anisotropy, the typical example is what we call an Ising model, which has a Z2 symmetry, namely all the spins can be flipped simultaneously, or an XY model, which will be a magnet with easy plane anisotropy, or a superfluid. The symmetry is U1 in that case, and the order parameter is a complex field, and so on and so forth. There are many examples of this. Okay? And so this goes back to work and in the classification proposed by Landau in the mid-30s, actually, in terms of the concept of an order parameter, which is a local operator that in the broken symmetry phase has an expectation value. And typically the broken symmetry phase is not one phase. There are many possible states, many possible ground states, which are related by symmetry, because the order parameter transforms under the symmetry. Okay? So for instance, in a magnet, it's the local magnetization, and then you flip it, say in the case of an Ising model. In that case, the ground state is degenerate in the thermodynamic limit. There are two states, okay, and Typically, the way you do it, if you want to make a magnet, you cool in a magnetic field, you do field cooling. Below the transition, you remove the symmetry breaking field, and then you end up in the broken symmetry state. And which one you pick depends on how you do this. Okay? So that's typically how that works. So in the field theoretic language, there will be some Lagrangian or some free energy, depending on how you want to call it. So here is, I don't see the, Oh, I'm committing suicide. Okay, okay, there we go. Okay. All right, so typically the order parameter changes. In this case, is Z2 as an example. So there is some term that depends on the gradients of the order parameter, and if this is as a function of time, this is written in the Minkowski signature in imaginary time here, because that's, you can tell because of the sign here. And so this may be in many possible dimensions, and this may include the time dimension or the imaginary time dimension if you're looking at the quantum case. And there are two types which are basically very similar. They are thermal phase transitions as a function of temperature, or as a function of a coupling constant or some parameter, there will be essentially a quantum phase transition. So for instance, an example is an Ising mode in a transverse field. As a function of the strength of the transverse field, you can go from an order phase to a disorder phase. Okay? So typically the expectation value of the order parameter is non-zero below the critical temperature, or below the critical coupling, and then it evolves in some fashion with some interesting universal behavior if the transition is continuous. Okay? So I will not talk about that. That's a very vast language of critical phenomena, which is very interesting, but it's not the purpose of the talk today. Okay, so that's what a conventional phase of matter looks like in broad terms. Okay. Oops, the other way around. Okay, so in the case of an SPT, or symmetry-protected topological phase, the first place, it doesn't have a local order parameter. If you look in the bulk of the material, there is nothing that happens that is of any interest. Okay, at least to me. Okay, maybe to other people there is a lot of interesting stuff. Okay, so no symmetry is spontaneously broken. They have a symmetry, but the symmetry is actually intact. It's important to that. And in particular, local operators have vanishing expectation value in a real sense, after normal ordering, if you want. The ground state is actually unique in this case. So it's almost the opposite. It actually looks like a disorder phase. In that sense. It is. But unlike conventional disorder phases, they typically have edge states which are protected by symmetry and by something we are going to call a quantum anomaly that I will describe in a moment. Okay? So examples of this, in this case, the symmetry is charge conservation, in the associated group is a group U1. It's a two-dimensional electron gas in a magnetic field. You have Landau levels in that case, and typically there is a field that contains the electrons in the sample that makes the Landau levels bend. And so if you have a Fermi energy here, remember the Landau levels have an extensive degeneracy, which is equal to the number of flux quanta going through the system. I'm thinking of the two-dimensional case here. Okay, so these are the degenerate states. Near the edge of the sample, these states get lifted, so to speak, already in first-order perturbation theory, you can see that. And then you see the states that actually cross the Fermi energy. These are going to be the edge states. Now, what is useful to look at this from the top-down point of view, here is the electron liquid. This is the boundary of the state. And because there is a potential that is keeping the electrons in, the electric field is pointing in, and there is a magnetic field out of the way. So there will be a drift velocity associated with that. And these electrons that live on the edge, essentially they basically go around this merry-go-round only in one direction, so they are chiral. They cannot go backwards. So for instance, if you put impurities, the states cannot be localized because there is no backscattering. Okay? because they are very robust states. So if you put an impurity on anything they do, they just go around it, they skirt it, okay? And this state in the book is actually a gap state, which is incompressible. Okay, so any excitations, if you want to add or remove an electron, will cause some finite amount of energy. The only place where the energy goes to zero is precisely on these states which are actually gapless. So they are gapless chiral fermions. I'm going to discuss this in some detail in what follows. Okay, so you have these chiral edge states. So this is the prototype. Okay, is the integer quantum Hall effect. Essentially is summarized by this. And it has a Hall conductivity, as you will see, which is connected to this number n, which is the number of field Landau levels that you have. So it's very simple. And the fact that there was some topology associated with this took some time to figure out. This was discovered by von Klitzing, which deservedly he got the Nobel Prize for this. And this, in particular, the Hall conductivity is so precise, is essentially the precision is in 1 part on 10 to the 9th in the better samples. So it's actually a better way to measure the fine structure constant than in any collider physics experiment. So this actually is the most precise way of actually measuring the fine structure constant. And nowadays it's used, for instance, for the standard of resistance and many other things. So it's used for metrology extensively. Okay, so what is a quantum anomaly? I'm going to do this in the most elementary case, electrons that live in 1 dimension, and I will assume that there is a periodic potential, so it's a very simple problem. You have a particle that is hopping from one lattice side to the next, and I will assume for the moment that it has periodic boundary conditions, so the support is a circle, so to speak. Okay? So classically, in a sense, a quantum anomaly refers typically to some symmetry that in some classical sense is actually protected, but is actually broken at the quantum level, that quantum mechanically cannot be respected. That's why it's called an anomaly. Okay? So the symmetry, when this happens, that symmetry cannot be made local, unlike gauge invariance, which is associated with the phase symmetry of the states, which can be made local by coupling, say, to the electromagnetic field. You have to make that symmetry a gauge symmetry in that case. In general, symmetries that actually have anomalies cannot be gauged, as people say. They are anomalous in that sense too. So the spectrum of this very simple problem is elementary, is taught in elementary courses. The energy as a function of momentum of the single particle states is a periodic function. The Brillouin zone is very simple. It's a segment with periodic boundary conditions, so it's a circle. And it goes from pi over a to minus pi over a being the lattice spacing. And the energy essentially at some point will cross a Fermi energy, which I set it to 0 in this case. And there will be 2 Fermi points, as you can see, 2 places where the energy crosses. You can see here that the slope is positive, and there the slope is negative. That means that these excitations move to the right, and these excitations move to the left. There is some echo. I don't know. Does it bother people? I can hear an echo when I speak, but okay, so this is very simple. So the vacuum, the true vacuum of the state, so it's a field Fermi C, okay? So you take essentially all of the so-called negative energy states, the states below the Fermi energy, you fill them up, and this is your actual physical vacuum of this non-interacting problem. This is the analogous to the vacuum, if you wish, of essentially the Dirac theory. It's very similar. Okay. So the symmetry, this theory has only one symmetry, which is a symmetry of changing the states by a phase. And this phase is defined modulo 2 pi because it's a phase. And notice that this phase is constant, it has to be constant. So it's a global U1 symmetry, and this symmetry gives rise to charge conservation. Once you have the symmetry, there is a conserved current. You can use Nether's theorem if you wish, and there will be another current here, which is essentially the charge current in the system. It also has translation invariance, because you can essentially relabel the sites by essentially one unit, if you wish. You can shift them, Cn to Cn plus 1, and this symmetry in the periodic boundary conditions is actually a symmetry. Of course, the edges, if you actually have open boundary conditions, is actually violated at the edges. Okay, so that will be important. In momentum space, you can do a Fourier transform of this. It looks like this. So this is just a number operator for electrons with momentum p, and the energy measured from the chemical potential, which is the Fermi energy here set to 0. The energy in this case is just minus 2t cosine p. I set the lattice spacing to 1 here when I do this. Okay, in the low energy limit, so as you can see, much of the time, if you try to promote states which live deep in this Fermi sea, you have to spend a great deal of energy, you have to go across this. But states which are very close to these Fermi points, it costs very little. In fact, in the thermodynamic limit, the density of states is finite, and then you can essentially get states with arbitrarily low energy. So you can decompose, the important states are those near these two Fermi points, kf and minus kf. And so these local operators, C of x, can be essentially Fourier transform, if you wish, or decomposed into a rapidly varying phase associated with the momentum, but essentially near the Fermi wave vector, and here the negative, and a slowly varying field that describes precisely these right movers, and the other one that describes the left movers. Okay, so you have two fermionic fields. You can join these two fermionic fields into a bispinor, a two-component spinor, where the upper component, say, is a right mover and the lower component is a left mover. So I'm going to rewrite this as a Dirac theory for you. So the Hamiltonian is very simple. This is just the kinetic energy of the right movers. This is the kinetic energy of the left movers. And if you want, you can write this. There's, of course, a velocity here that you can choose your units to make it equal to 1. So this is, of course, in Dirac, this will be the speed of light. Here, the speed of light is a Fermi velocity. It doesn't make any difference from this point of view. I once tried to write a paper, one of the early papers, using this type of ideas in PRL, and one referee objected, saying that this paper is wrong because everybody knows that the fermions in a material don't move at the speed of light. So you always have to, referees belong to some other species, right? Except that it's us, but okay, some other. When we talk about the referees, there are some other species. Okay, so in the relativistic form, in the Lorentz invariant form, you can write it in the conventional Lagrangian, okay? And you can define your Dirac gamma matrices in terms of Pauli matrices. And notice that I used here, in principle, there are all three of them. But if in the Hamiltonian itself, only one of the Pauli matrices appears, essentially the sigma 3 matrix. But if I add the mass term, then I get another matrix, and there are two possible mass terms that I can write, as it turns out. And this is related to the symmetries. Okay, so there are two symmetries. In this low energy theory appears to have more symmetry than the problem I started with, which is this, which has only one symmetry in a sense, only one global, aside from translation invariance. This is also translation invariant. Okay, one is, of course, it has a charge phase symmetry. In other words, the global phase symmetry. So you take the spinor, both components, you rescale them by the same phase. And there's also a chiral symmetry, where you basically, gamma 5 I took to be the matrix sigma 3. That means that the upper component has a phase, and the lower component has the opposite phase. Okay, so this is called a chiral transformation. You can show that in the original problem, a chiral transformation amounts to a displacement of the density operator by some amount. And theta, the chiral angle, this chiral angle theta, essentially is related to the displacement that you do. There are operators you can write that break, essentially associated with the mass terms that you can add, that break the chiral symmetry. When that happens, the system usually has a modulation, the original problem, a modulation in the charge density, and in condensed matter physics, such systems are known as charge density waves. And they are associated with the spontaneous breaking of this chiral symmetry in that case. So for those of you who high energy physics, this is an example of chiral symmetry breaking, okay? These are simple examples of that. Okay, so the Dirac theory, the problem is it has, so why do we have more symmetry than we started with? The microscopic theory has only one symmetry, the effective low energy theory has a bigger symmetry, okay? So something has to give, okay? That's where the anomaly comes in. So, as you say, so there are let me find two current operators. I'm going to find it as two vectors. It's not a 4-vector because I am in 1+1 dimensions. So this is the density and this is the current. The density is essentially the sum of the density of right and left movers. And the current is the difference because if there are more particles moving to the right than moving to the left, there is a net current. Okay? That's very intuitive. And there is another current called the chiral current associated with the other symmetry, which in a sense is the Cauchy-Riemann dual of that, associated with this epsilon tensor. Okay? And essentially amounts to exchanging these two guys up to a sign. Okay? Now, both of them formally are conserved, okay? Because when you do this approximation, you're assuming that you can freely, so let me come back, let me actually, no, okay, there we go. Okay, so what you're doing is you're linearizing the spectrum here, and this will be the spectrum of the right movers, and here the spectrum of the left movers. In this effective low energy theory, in the Dirac theory, you take that to extend all the way to infinity. And you're assuming that the vacua, if you wish, the Fermi seas or the Dirac seas of the right and the left movers are totally independent. But in the lattice models, you can see they are not. They are connected through the UV, if you wish, because it's a periodic potential. There is always there is a band, and this band has a maximum and a minimum. So if I want to have more right movers and left movers, the excess of right movers has to come at the expense of the left movers because charge is conserved. So if I insist in charge conservation, which my lattice model has in a very explicit way, you cannot actually really work liberally with this chiral symmetry anymore. Okay? Okay, so this actually is associated with the anomaly. You can see that by doing the following. You couple this to an electromagnetic field. Oops. Keep placing the wrong place, okay? So remember you're in 1+1 dimension, so this vector potential has a space and a time component only. Of course, you're in 1+1 dimension, there is nothing transverse, so the only curls, the only field that you have is purely electric. There's nothing magnetic here. So the equations of motion, which are just a Dirac equation in this background, they can be written in this form and will work in the gauge A not equal to 0. And you can define the electric field as the time derivative of this space component of the vector potential as usual. Okay. Now you can compute the rate of change of the total number of right movers. And you can do a simple calculation, and you can see that it's proportional to the electric field. You can use the fact that the density of states is finite and constant, and the prefactor is E over 2 pi. If you calculate the rate of change of the left movers, you find that it's equal and opposite to that. Therefore, the total rate of change of the sum, which is the charge, is 0. Okay, charge is conserved. But you can also interpret this in the following way. You can say, well, the number of right movers plus the number of left movers has to be kept constant, say 0 if I neutralize the state. So that means that the number of right movers has to be equal to the number of number of holes, if you wish, of the holes of left movers are antiparticles. So this electric field gives you an example of pair creation. That's what is happening here. Okay, there you are seeing pair creation. On the other hand, if you can define also the chiral charge, which is here, but this is the negative of the other one. So in this case, they add up, and the answer is not zero. Okay, and this is the anomaly. You can write this in a more compact form as the divergence of this axial current is non-zero and is equal to actually the dual, so-called dual of the field strength with a coefficient which is E over pi. Okay. So this is the famous axial anomaly. Was discovered originally in particle physics in 4 dimensions by doing triangle diagrams and things of that sort. But you can see that it's very intuitive. Okay, that's where this simple example, you can see it in a very transparent way. Okay, so if you insist in regularizing the theory in a gauge invariant way, which the lattice model does, then the axial symmetry has to be anomalous necessarily. Okay, and so you cannot gauge it because a theory where the current is not conserved cannot be coupled to a gauge field. So it cannot be made local. Okay. So that's an important consideration to this. So the chiral current is not conserved. Of course, if there is a mass, if the theory has a mass, if there is a mass gap, there is an additional contribution here associated that comes from the mass. Which, of course, in the case of the mass, is not conserved because it mixes right and left movers. Okay? So it is expected. So this is a very simple case. Is this clear? This is a very simple problem, and it's the simplest example of an anomaly in this sense. Okay, let me look at an application of this, of a system with a broken global symmetry, Z2 symmetry, known as polyacetylene. So it's again a problem. So this is, for the chemists, this is essentially of carbon atoms with hydrogens as well. And I will draw it here as a system of balls and springs. The balls are the carbon atoms, the hydrogens are dangling there. Okay, and the system actually dimerizes, so that means that pairs of carbon atoms, they approach each other. Okay, so there are 2 possible ground states, depending how you pair them up. And that's how the system essentially works. It means that the hopping matrix element is now depends on where you are, because if they are farther away, it's going to be smaller than if they are closer by. And so what you do is you say, well, the hopping matrix element that before was constant now has a term with some coupling constant proportional to the local distortion or displacement of the atoms. U sub n is the displacement of the nth atom. Okay? And this actually gives rise to, is like a mass term in the continuum model, but it's a mass term that depends on an order parameter, which I'm going to call phi, associated with this distortion. Okay, this number. So when the distortion is non-zero, you get this order parameter that breaks the Z2 symmetry, and typically will be some penalty associated with this. Okay, so this was studied in the late 70s and early 80s by many people. It has been rediscovered it's actually one of the simplest examples of an SPT. Okay, so the mass term is essentially psi bar psi, usually in Dirac mass term. So you create the right mover and you remove a left mover and vice versa, so it's Hermitian. There is another possible mass term that involves a gamma 5 matrix, which has a minus sign here and a factor of I. There are 2 possible mass terms. The one particle Hamiltonian, so essentially you can see phi going to minus phi can be compensated by changing this fermion bilinear, changing the sign, and that amounts by multiplication by a matrix gamma 5, which was a matrix sigma 3. So essentially it's a sign that you're changing. So it's like an Ising symmetry, Ising, sorry. The one particle Hamiltonian is very simple. It's P and minus P are the diagonal part, associated with this part. And then there is this mass term, the mass being essentially this factor here if phi is constant. The spectrum is well known, is the usual relativistic type spectrum with the gap. Okay? And the expectation value of phi naught, which I'm going to call phi naught, in this case, it turns out this is non-perturbative. It has an essential singularity. This theory, as it stands, so here sigma is the spin of the electron that in condensed matter typically is a label. Essentially, there are electrons we spin up and electrons we spin down. And in this mode, if you integrate out phi, you get a quartic term, and it's known as the Gross-Neve model in particle physics, which was an early model, a model proposed in the 1970s for chiral symmetry breaking, in fact. So this is an example. In this case, the charge density wave is commensurate with the lattice, and the symmetry is discrete. You can also have a case where it's incommensurate and has other properties which are interesting. This theory is asymptotically free, okay, for those of you with high energy background, and this is manifest in the form of this essential singularity that enters in the gap, in the mass gap. And there is a prefactor that you can get. Okay, now let me consider the case, same problem, and this actually was the interest in the late 70s and early 80s. What happens if so there are two inequivalent states. So imagine I have a domain wall between these two inequivalent states. Okay? Or it's an antiphase. In this language, it should be called an antiphase domain wall, or a boundary which will play a similar role. So essentially, a domain wall essentially is taking my mass, which is g times this order parameter, going to assume that phi essentially goes from some value, which is the negative of the expectation value, to the positive of that, and it will go continuously. So that's a domain wall. So here there will be a domain wall and an anti-domain wall. I'm going to call them a soliton and an anti-soliton. Now, if you look at the single particle states, the Hamiltonian now has this mass gap that depends on position. Okay? You can solve this problem. It turns out it has propagating modes, but more interesting is the fact it has zero energy modes, which are normalizable. Okay? And the spinor that essentially, the normalizable spinor, which is an eigenstate of this with zero energy, is given here. So it doesn't depend too much on what the dependence of this mass on position is, except it has to go to a constant at infinity. So roughly speaking, this is proportional to the length times the expectation value, if you wish. Okay, so it decays exponentially. So the state is, there's a state that is localized here in the place where the order parameter changes sign, so at the soliton, and similarly there will be the other state that is, in this regime here is unnormalizable, there is a normalizable state in the other case. They have opposite charge, okay? Now you can calculate what happens to the charge density. In the ground state, the charge density is 0. It turns out there is a charge of minus the electric charge divided by 2. So it's the first example of a fractional charge that accumulates near this point. And the opposite value at the other end, because the total charge has to be conserved. So you have, the soliton now has peculiar properties, has a fractional charge. Now in reality, there is spin. So this analysis is correct if I ignore the spin. If we have spin, essentially will be 2 electrons that will have essentially charge E over 2. And so you can actually, so in fact, you're going to see a boson with charge E if you doubly populate that state. Okay, so people tried in the early days doing experiments in this essentially organic material, which is polyacetylene. It's a very complicated, very dirty material, as it turns out. And people tried using nuclear magnetic resonance and many other things to investigate this problem. They could never get it to work. Okay? Still somebody got a Nobel Prize for it, but that's a different story. But not for the experimental part, okay, for discovering these one-dimensional conductors, Alan Giger did, okay. So now, if you have open boundary conditions, on the other hand, the boundary condition actually breaks this Z2 symmetry, as I said. And so in a sense, you're going to have basically like a soliton sitting at the end, sitting at the edge. And then you have this fractional charge that will be sitting at one end and opposite at the other end. So for the system to have total charge being conserved, there has to be a polarization. The ground state is now polarized in that sense. So the bulk, there is nothing interesting again, but there is some polarization charge in one end and the opposite at the other end. Okay? So this is a simple example of that. Is this clear? Somebody has to tell me, oh, it's 10 already. I talk too much. I'm not sure how much, yes.
Can't you think of the polarization as a local marker?
But it's more global than local, because it's only detectable at the edge. If you look in the bulk, there's nothing. I mean, a polarizable medium, certainly, but we'll need to spend some energy to polarize it. And
The value of the polarization in the bulk.
is zero, okay. Yeah, you cannot observe it. You have to go to the edge to see it.
But the polarization is not zero, right? It's one half in the right units.
At the edge, but in the bulk, there is no polarization. The dipole moment in the bulk. Yes?
If you have this wave function that you show for
Yeah.
the soliton, what is the Chern number? Can you calculate?
There is no Chern number here because the symmetry is Z2. I'll come to Chern numbers in a moment, okay? Okay, it's a topological invariant, but it's not the Chern number. Okay, so let me now go to the integer Hall effect that I already sketched for you. Here, I have a cartoon for that. Here. I want to revisit that problem. Here we go. Okay, so imagine now that the electrons are confined in a region that has the geometry of a disk. And I'm going to make this disk actually an annular region that is going to have a small hole essentially inside where the electrons cannot come in. And then the two-dimensional electron gas lives over here. There's an old argument, famous argument by Laughlin called the gauge argument. So you can imagine now inserting an infinitesimally thin solenoid that carries some flux, and then in particular interested when that flux is equal to the flux quantum. So if you insert, so this is an example where the Aharonov-Bohm effect has to work, okay? So when you insert this flux, essentially there is an EMF that has to be induced. So there is an electric field that appears in the bulk as a result of that, because it's time dependent. And that generates a current, which is actually the Hall current, that actually goes from one edge to the other edge. And then Laughlin showed that in that case, it's just one electron at the time, is an integer in this case. Essentially, it's an integer number of electrons that move from the inner edge to the outer edge, these two chiral edges. So this is an example. Again, in this particular case, the current in the bulk is actually locally conserved, but is not conserved when it reaches the edges, okay, because it's an end. So there is actually a problem with current conservation. Of course, it's compensated by some charge, and because this is chiral, there will be some current associated with that at the boundary, and similarly at the inner boundary. So this is an example of what people call the anomaly inflow. The charge current is actually anomalous in this case. There's a gauge anomaly in the system, which is compensated by a similar gauge anomaly as you will see at the boundary. So this, in this case, the anomaly is that the charge conservation is then again satisfied in a global sense, not in a local sense. This is not working for some reason. Okay, well, let me just, maybe decide I should stop talking. Okay, now I will talk about Chern numbers, which is related to this problem. So this goes back to Bloch. So Bloch essentially showed that in a periodic potential, the states essentially are bands, and they are classified by these Bloch states, which have a label here is a band label, and a momentum, and the momentum is inside some Brillouin zone, which is a torus in momentum space. All I'm going to say today is in 2 dimensions, so the torus is a 2 torus, a product of 2 circles. Okay. Each state, of course, in quantum mechanics, a state itself is defined up to a phase. The phase is arbitrary, it's not observable, but changes in phase are observable. So in principle, you can redefine the states by a local phase that depends, maybe different for different bands and different momenta. They are physically equivalent. They form a ray or a bundle. And if you take 2 states, say 2 points in the Brillouin zone which are nearby, this state essentially will be smoothly related to the other, and there will be a rate of change, which is this derivative. So this defines what people call a connection. It's called the Berry connection, which is the inner product of the change with the original state up to a factor of I. So there is a time derivative here. And again, if you make this transformation here in the states, this connection, the Berry connection, changes as a gauge transformation. So this looks like a gauge transformation in momentum space in some sense. Okay? Of course, things which are related, as usual, by gauge transformations are physically equivalent. The only things that matter are those things which are invariant under gauge transformations. And this is what is called the Berry curvature, which is the curl of A, essentially written here explicitly. In this sense, it's invariant under this transformation. Okay, now let me note, I don't think I have time to go through this, but what this actually means is that if you're going to have, so imagine that you want to consider the entire Brillouin zone, and let's say gamma is the boundary of these 2 torus, so then you used to do the repeat. Suppose you want to have a total flux going of this Berry connection to go through this torus, then in principle this is not possible, because if you have periodic boundary conditions, then the total flux will have to vanish. So the only way that flux will be non-zero is actually if there is essentially some singularity. So in other words, if this vector potential will have to have some non-trivial winding around some particular point or points. Okay? So in particular, this winding number, which you can define, is actually going to be your Chern number, as you will see in a moment. So this, when this happens, you can imagine that there is some point K naught where the state has to go to 0, because for this to wind, the state has to vanish at some point in momentum space, at least one point, let's say K naught. And let's say you have region 1 in the Brillouin zone which does not include that, and there is another region 2 with some boundary, which is essentially where the other state is 0. Of course, I can define my block states here and there, but they cannot be smoothly connected anymore. This is the issue, that they are not globally well defined. When you come to this common boundary, they have to differ by one of these gauge transformations. And for this to have a non-vanishing circulation, the gauge transformation has to have a non-trivial circulation around this common boundary. And that circulation is precisely the Chern number. Okay, so this is this particular formulation, I think, was done by Mahito Kumoto in the context of the quantum Hall effect on the lattice, but it's a general problem. Okay. Okay, so you can imagine now a state that I'm going to call a Chern insulator, which doesn't have an external magnetic field, but the Hamiltonian, for reasons that have to do with microscopic physics, breaks time reversal symmetry. So a simple example is an example that was constructed by Haldane. Well, essentially, it's a version of graphene. In 1988, graphene didn't exist, so it was still two-dimensional graphite at the time. And except that he added additional hopping terms with essentially interesting phases, so there will be some non-trivial fluxes through these triangles in such a way that the total flux added to 2 pi, which is equivalent to 0. So in the case of the integer Hall effect on the lattice, this was studied by Thouless, Comboto, De Nijs, and Nightingale. They showed that if you have, there are these Chern bands, which they classified. So these are so-called the TK and N integers, and that's how they were called at the time. And the whole conductivity essentially is the sum of all of these integers of the occupied bands multiplied by E squared over H. Okay, and this comes from doing essentially a simple linear response calculation. And in this case, this is essentially, in the case of the integer Hall effect we discussed before, is the same. And the parameter nu, which is the filling fraction, which is an integer, has, in a sense, is essentially, in this case, all of these c's are equal to 1. Now, in this other case, it turns out you can have what is called nowadays the anomalous quantum Hall effect. Anomalous in the sense that there is no magnetic field, but it's based on this graphene problem in Haldane's formulation. So in graphene, there are the Brillouin zone is also, graphene is defined on a hexagonal lattice, and the Brillouin zone is also hexagonal, and there are in equivalent points, K and K prime. So K has 2 images by symmetry, and K prime also has 2 images by symmetry. And this is reflecting the fact that there are 2 sublattices in graphene, A and B, and the Hamiltonian now looks like this in this language. And in graphene itself, these points K and K prime are special. That's a place where the bands cross and the gap goes to 0. So you can define an effective 2 plus 1 dimensional Dirac theory, essentially that is essentially by focusing on the low energy regime, much like what I do in 1D around these points. But they come in pairs. I will finish in a moment. And this is related to a famous or infamous problem in lattice gauge theory, that if you try to discretize the Dirac equation, they always have doublers, okay? Which is one of the problems for people that want to do chiral physics, essentially for chiral gauge theory, for instance, and things like that in lattice gauge theory. So they come in pairs, okay? And so we're going to see that the pairs actually do something interesting, and discussing this I will finish. So there will be 2 species of 2 bispinors. We'll call them psi1 and psi2, essentially associated with K and K prime. And they couple to the external electromagnetic field in this form, as usual. So you can calculate the effective action by, say, integrating out these fermions. You can do this in perturbation theory only. And so at low energies, it will be the exponential of a bilinear of the gauge fields with a polarization tensor stack here. And this, because of gauge invariance, this has to be conserved, so the divergence has to vanish. So there are, in momentum space, this tensor has 2 independent tensors. This is, which is parity even, and there is a parity odd tensor that appears. Okay? So when you write down the effective action for the electromagnetic field, you get from the parity even part something that looks like essentially the Maxwell piece of the Lagrangian, with some effective mass that depends on the magnitude of the masses associated near the points K and K prime in Haldane's model. And the other term turns out that the prefactor that will appear here is actually the whole conductivity, because this term breaks time reversal symmetry and parity. And in this case, the Hall conductivity is essentially E squared over H times the average of the signs of the two masses. Okay? So let me explain that, and with that we will finish. There are two possible phases that result and a quantum critical point. There is a trivial insulator when the masses are equal and opposite. So essentially you have one mass and the opposite mass. The Chern numbers are equal and opposite in that case, and they add up to 0, so the sigma xy vanishes. On the other hand, when they are equal, these two guys, remember this comes with the peculiar factor of 1/2, which is not allowed for Chern numbers, has to be an integer. This is a half integer. Okay? But in that case, they add to 1. And so in that case, now the band, associated with the gap state, has a Chern number which can be 1 or minus 1, and the Hall conductivity is plus or minus E squared over H, depending on how you do this. And this has been seen, this is an anomalous quantum Hall effect. This has been seen experimentally. Well, there were other sightings before, but they were questionable. But now this has been seen very clearly a few years ago in twisted bilayers of molybdenum and ditelluride. Okay, so this is essentially a physical realization of the anomalous Hall effect. So it's no magnetic field. But imagine now I come and tune one of the masses so that the mass M1 is 0, but the mass M2 remains non-zero. So I can go from state 1 to state 2 or vice versa, right? That's a phase transition. The gap closes, that's a hallmark of a phase transition. Something is going massless. But the Hall conductivity is non-zero, but it's 1/2 of what it was before. Okay, so there is a quantum critical point where you get precisely this half quantized value. But this actually, as you can see, comes from the so-called doubler, which is actually deep in the ultraviolet for the high energy people. Okay, it's a massive term, and it breaks time reversal, so it has to have a Hall conductivity associated with that. So this is an example of a topological phase transition in this sense. Okay. Well, maybe this is going to be the beginnings of my lecture tomorrow. Okay, so maybe it's a good point. The chairperson here is going to kick me out. Okay.
Well, we have some time for a few questions.
Yes.
Thank you. With respect to the first example, this one-dimensional binary structure.
The one-dimensional case? Or the
yes, the first example.
The first example, yeah.
In the diagram, you put the Fermi level more or less in the Hall filling. That is a...
It's special. It doesn't really have to be.
It's not a condition?
That's not important.
That's not relevant.
You can put where you want. There are still right movers and left movers.
Okay.
But there is actually an important difference. In the low energy theory, you can still have a CPT theorem because you can still have charge conservation relative to that level. But on the microscopic level, if you don't put that at 0 at the symmetric point, the microscopic theory is not charge conjugation invariant. Okay?
I see.
So in condensed matter physics, one should be careful about the use of charge conjugation symmetry. Okay. Because it's a special symmetry for the lattice model. It's non-generic, and it can be violated easily.
Okay, okay. My other question is in the case of the Brillouin-Son for the topological band structure.
Yes.
You mentioned that we have a torus in the K space.
Yes.
My question is, this torus, the system is one-dimensionally? That
No,
is not clear. It's two-dimensional.
That's why I have Chern numbers, yes. Yeah, I should have explained this.
Okay.
Because the torus is two-dimensional, you have a map of the torus into the, if you wish, torus of boundary conditions of this problem, if you want to use that terminology. So there is actually an actual invariant, which I will discuss next time. So there is a homotopy, which is defined by homotopy. But the other way you can think about it is precisely, this went a little too fast, is essentially the winding of the gauge transformation that defines the wave functions in these two patches. If the gauge transformation have a non-trivial winding number, in other words, if the circulation of this gauge transformation, which is the difference of the two vector potentials, doesn't add up to 0, then necessarily you need to have something funny going on inside.
Okay. My last
So it's like a vortex.
My last question is, this analysis can be applied if the system is one-dimensional?
No, because in one dimension the symmetry is, this topological symmetry is discrete, is Z2. So there is a larger classification that essentially, in some cases the symmetry is discrete, Z2, in other cases is U1 or Z associated with this. So it depends on the dimensionality, and there is a periodic table that people wrote for this. Okay. Thank you very much. Yes?
You mentioned that the topological states or edge states are basically very close to the Fermi point.
Yes.
And I was wondering if, for instance, in these solid state systems that I described typically by the time-binding models,
Yes.
it is enough to see the topology of the system just analyzing the low energy limit around the...
Yes, because it turns out that if you do it more carefully, it's a property of the entire field band that enters. So in the case of the Chern numbers, the Chern number is a property of the entire band. We're going to do something tomorrow where I will actually look in regimes very close where the bands are about to cross, and you can see that in that case, which is where these 1/2s come from, in that case, essentially, this half of the Chern number is provided by one particular point, and the other half is provided by the other, and the rest of the band doesn't contribute much. But in general, it's a property of the entire band. So you can go to the regime where the gap is very large, and so this low energy theory is inapplicable in that case, and still you have the Chern number. Okay.
Thank you. And
Yes.
can I do another one?
Yes.
And the other question is that from the mathematical point of view, there is further Chern numbers.
Yes.
Do you know if...
In 4 dimensions they appear.
Well, but I think there is second number, Chern number, also for this two-dimensional case. But my question is if there is another physical quantities further than conductivity.
Yeah, typically this involves a non-abelian symmetry, in fact. Okay. So in the case of Shuji and Zhang actually looked at, who died a few years ago, looked at the case of the 4-dimensional Hall effect, and there is the second Chern number that enters in that case. You can then use some dimensional reduction by compactifying one of the extra dimensions, and then you can reduce that to the integer, to this Z2 case. So in that sense, you can go, somebody asked me if Chern numbers actually play a role in 1D, you can take the two-dimensional problem and wrap it into a cylinder and make the cylinder very small, and then you can go to the 1D case. So if you are a string theorist, that's not a problem because I do that all the time. But so here I have to imagine that you're thinking of the 1D problem as a very thin tube, essentially.
Okay, one last question here.
Yes.
Thank you for the presentation. I wonder if you could clarify the argument on periodicity on polyacetylene.
Yes.
When you went for that polar, what you get is, it looks like a polar metal, but I was confused as to how that periodicity
It's an insulator.
works.
It's an insulator, not a metal.
Okay, I see. Okay. Then it
because there is a
still
gap,
works.
okay?
Right, okay, I see.
Yeah.
Okay, thank you.
Right. In the case where it's a metal, which is in the incommensurate case, there is more interesting because there is actually continuous current in that case, but not in this Z2 case. Yes.
How do you put the charge? Because, you know,
No, you can, no. In that case, there are no edge states. If you have periodic boundary conditions, you have just two possible ground states. That's all. Then you can have a soliton and an anti-soliton. Okay, that you can do. And that's so you can have periodic boundary conditions, put a soliton here, the anti-soliton there, and then you wrap it. But if you have open boundaries, you can have the soliton and the anti-soliton sitting at the endpoint. Okay.
Okay, well, thank you very much. We thank Professor Fratkin again.
La flecha dejó de funcionar.
No funciona muy bien.
La flecha dejó de
A ver,
funcionar.
ahí, vamos.
La flecha dejó de funcionar. Sí.
So our next speaker is Gerardo Naumis from Instituto de Física de la UNAM, which is going to talk about revisiting the time-driven origin of topological phases and its importance in solid-state physics. So welcome.
Ok, dice que no funciona la flecha, no sé.
Creo que lo cambiaron.
Ah, ok, ok.
Ahorita que empiece a hablar, le subo el volumen.
Sí, ok. Thank you very much. First of all, I would like to thank the organizer, Luis, Alberto, and Eduardo. Where is Eduardo? I don't know. For the kind invitation to give a talk in this very nice workshop. And today I'm going to talk about the time aspects of topology. And I will try to convince you that many of the topological features are related with this interesting, the physics of a very simple swings. This is in Mexico in the mountains. You can have a swing that is called the swing in the clouds. And sometimes we forget about the time origin of the topological phases, and this is very important. We are going to see, for example, for the case of graphene and Dirac materials. So let me start by, la flecha creo que funciona. Okay, so the outline of my talk is the following. First, I'm going to talk about the topological phases, and especially about the condition of adiabaticity. Then I'm going to talk about time-driven problems in topology, and some application to 2D materials, some conclusions, okay? So most of the things that I'm going to talk in the first slides were touched in the talk by Professor Eduardo Fratkin, and basically, why topological phases are useful? Because they characterize states of matter. It's a useful way to characterize a state of matter with certain physical properties, when in many cases are useful. So the most paradigmatic example, and was really one of the most ignition sparks for this field, is the quantum Hall effect. When you have a quasi-two-dimensional material, in this case is a field effect transistor, so you apply a constant magnetic field. Here you have an electric field in this direction, so you get a current, and due to the Lorentz force, you will have that the charge carriers are deviated, so you will get a voltage in the perpendicular direction. So if you look at the conductivity in this direction, when you have an applied field in the x direction, you get that they are related by this number that is called the conductivity. And it turns out, if you measure the inverse of this quantity, which is the resistivity, it turns out that it's quantized. And this was measured by von Klitzing, and he won the Nobel Prize for this in the last decades of the 20th century. And eventually it turns out that these jumps, they were related with an integers of which are related with some topological invariant, which are called the Chern numbers, okay? So how this was explained by Thouless and others, this was explained. So the typical calculation that you do in solid-state physics is you can do it in two ways. Either you start with a two-dimensional gas of electrons. It's very special. you cannot have it in 3 dimensions. You need 2 dimensions. So you apply the magnetic field, and you can solve it as Landau did. Basically, you propose a gauge. This is called the Landau gauge. That is the simplest one that will give you the magnetic field. There are other gauges, for example, the symmetric one. But you solve this equation, which is basically a Hamiltonian of free particles with this vector potential. It turns out that these Hamiltonians can be written as a quantum harmonic oscillators. So the levels of these problems are the levels of the quantum harmonic oscillation. These are called Landau levels. Or you can also solve this problem as Harper and Hofstadter did. Basically, you consider that the electrons lives in a lattice, and this lattice you have a distance between the atoms, and this introduces a new length scale in the problem. So in this case, when you solve this problem, you will get that there appears a quantum flux, which is h divided by the charge of the electron. In this case, the interesting thing is that there is a competition between this elementary quantum flux and the flux that arrives from the fact that you have a unitary cell. So the flux is the magnetic field multiplied by the area. So this is the important quantity with the ratio between them, okay? So with this ratio is a rational number, you can solve the problem using the Bloch theorem, because it turns out that this problem can be mapped into a Harper equation. The Harper equation is like a one-dimensional discrete equation with some potential that is periodic, and where you have this field here. Okay. So by the way, this is the equation. It's like a discretized equation that describes a swing, which is a parametric pendulum. We will talk a little bit about that. Okay. So the fact is that this was solved by Hofstadter. So basically, you have a periodic potential. Okay, you have a periodic potential. Okay, you have a Hamiltonian that is periodic. So therefore, you can use the Bloch theorem when the flux is rational, of course, because if not, this problem it's quasi-periodic. It's very complicated. Anyway, what you get is the solutions is made from a plane wave multiplied by a function that has a periodicity of the lattice. So if you plot the spectrum, as Hofstadter did, so basically you have here the energy, here you have the ratio between magnetic fluxes, and you get this very nice fractal, which was the first non-fractal in solid-state physics, where the black dots are allowed states. So, for example, if you look at a given flux, let's say here at 1/3, for example, or any flux that you want, you will see that you have a band, then you have a gap, a band, a gap, and another gap, okay? So for example, you fix the magnetic field, you fix this flux here, and you can explore this direction of the spectrum just by biasing the system. Just like, for example, with a substrate, you produce holes or whatever. But the thing is that when you do it in this way, you will find that the system is an insulator. It will not conduct. However, Thouless, Komoto, Nightingale, and the G's, they use the Kubo formula to calculate the conductivity, okay? And eventually they realized that this was related with some topological invariants. So the thing is that eventually it turns out that what happened is when you cut the system, when you have this periodic boundary condition, will not conduct. But when you cut the system, you will get this H state that Eduardo was talking about. And basically what you see when you do that, in fact, is when you have the bands, but you get states that traverse the gaps. So this is an actual calculation that you can do very easily with MATLAB or Mathematica. These are the bands of the quantum Hall effect. When you cut the system, you get this state that traverses the gap. And it turns out that if you look at the spectrum, in fact, these states lie here in the gaps. So you have many combinations, and all these gaps, they have a different conductivity, and they are like different quantum phases, topological phases. For example, in this region, your Chern number is 1, and the next is 3, 5, and the other you see 2, 4, 5, 6, and forget about the sign here, but you have very complex patterns here. So this is like a quantum phase diagram when you put the numbers inside here. And the way that usually solid state physics we work in the following way. We calculate the spectrum, the wave functions, and then we build the very connection, which is this derivative of this part of this periodic part of the Bloch function. From there, we calculate the curl, okay? And from there, we just calculate a trajectory. We calculate this integral of the very curvature along a certain path, closed path, and from there, we get these Chern numbers that are here, okay? And this is the typical thing that one do in solid state physics. Professor Eduardo Pratt can explain all this, why this happened and so on, okay? So this is more or less the same thing that he presented. But, by the way, just to tell you that it was thought, when Hofstadter did the thing, it was thought that it was not possible to measure this spectrum because lambda level correspond to very weak fields, and that's where von Klinzit measured the quantum Hall effect. But it was thought that it was not possible to measure this part of the butterfly because you need a very strong field. However, when graphene was discovered, it was found that if you put graphene on top of another lattice, and this lattice has a different lattice parameter, you can build a huge superstructure, so you can get unitary cells that are huge, of 100 nanometers. Okay, maybe I should, like this? Maybe it's better? Okay. So, so they were able to measure this Hofstadter butterfly, and this was it was measured in 2014, so it's more or less recent, and it was possible because of these advances. Okay. However, if you look at the topological properties, and in the original works, for example, of Berry and Thouless and so on, you will find that, in fact, the origin of topology was based on time perturbation theory. So, for example, if you look at the Wikipedia entry for Berry and geometrical phases, which in many books start with the same things, you consider a Hamiltonian, and your Hamiltonian depends on certain parameters, on a vector, that you put all the parameters in a vector, and then you start changing these parameters as a function of time. So usually you have, for example, some space of parameters, and you move your Hamiltonian in this, as a function of time, you move the parameter. So it's kind of transporting the system. Usually they say that, okay? So now, if the system, if you make this perturbation adiabatic, or you move this parameter in a adiabatic way, okay? And what does it mean adiabatic? That's the thing that we are going to answer in the next slide, but of course means that somehow the velocity on doing that is much less than certain time scales that the system has, okay? So the thing that Berry did, and Thouless and others, is that the wave function as a function of time is given by this thing. You have one part of it is something that is called the instantaneous evolution, which is basically you solve the time-independent Schrödinger equation, so you get an eigenvector that just is, that you obtain by neglecting the time derivatives, and you use just the stationary Schrödinger equation, and then with a certain energy that is called the instantaneous energy. So this will give you something that is called the dynamical phase, that is not related with the geometry, of this space of parameters, or the connection is also known, but eventually you also get this phase that is here. So how do you get this phase? You can prove that this phase is given by the rate of change of these instantaneous eigenvectors. Okay, so you make this integral, and using the fact that you are parameterizing your parameters as a function of time, you can replace this integral over time as a function, as a closed integral in the parameter space, okay? and you calculate this. So usually these results, you say that the very phase only depends on the path in the parameter space, not at the rate on which the path is traversed. So this is very nice. So in solid state physics, sometimes we forget about this, all these things, and we just get this thing, replacing, for example, this parameter as the momentum, which is in the K space, in reciprocal space, which is nice, okay, very nice. But what does it mean as adiabatic? Adiabatic condition means that if you have, for example, two states, okay, and these states are separated by this energy, when you apply a perturbation, your perturbation needs to be such that you don't make transition from this state to the other, which means that basically the frequency of your perturbation, for example, you have a wave, an electromagnetic wave, for example, is less than the gap. That means that you cannot absorb a photon, for example, to make a transition. And in fact, one of the classical results by Thouless is that you don't get transition, but you get a certain shadow of the evolution of this state into the upper state, okay? So basically, you get that your evolution can be written as the dynamical phase that is here. You get this instantaneous eigenvector, but you get a projection in the upper state, okay? And this is the thing that will produce this topological phase, this thing, okay? This is a classical result by Thouless in Physical Review B, 1983, okay? But this is very nice, but what happened? Let us consider, for example, the case of graphene. So this is a usual calculation. You have graphene, as it was explained also by Professor Eduardo Fradkin, is a two-dimensional material made from carbon atoms in a honeycomb lattice. If you make, for example, a calculation of the band structure, you will get this. Here you have the energy, here you have the momentum, and you have this very nice structure. And the Fermi energy, as the orbitals of carbons are half-filled, are at the middle of this, and they touch in a region where the energy dissipation has the form of a cone. So you can describe this system as an effective Dirac theory. It's basically, this is the same idea that he explained for the one dimension, but this is the same thing. And it turns out that the Fermi energy is here. So if you proceed in the way that I said, for example, you take the eigenfunctions of this system, you calculate this the very curvature and the very connection like this, you take the eigenvalues, eigenvectors of the Dirac Hamiltonian, and you get the result, and then you make a closed path here, and you get a number. And this is nice, you get a number, which is your phi is pi. If you do it in the another Dirac inequality coin, is minus pi. But the thing is that if you think a little bit, you will see that there is no gap. So the adiabatic condition is never met, okay? So that's a problem, because we started saying that the very phase you need to have an adiabatic conditions. So one way of thinking is, okay, let's modify the system and open a gap and see if there's happened, but this is a little bit tricky, no? What does it mean adiabatic, okay? And this problem. But of course, and there are also interesting this time problems, because there are many interesting things about engineering the time properties of this system. For example, here we have two examples. We have graphene on top of something that is vibrating, and here you measure the conductance, so the conductance vary as you produce oscillations in this membrane, okay? So you wonder what are the topological properties, for example, of this time-dependent problem. Well, there's this very nice problem. You have graphene here, you have these electrodes, you shine it with light, and this will affect the current here. This is called a photocurrent. For example, in this case, you can produce when the polarization of this wave is circular, the current goes in one direction, but if you use linear polarized light, it goes in the other direction, okay? So you can change the charge carrier here just by changing this, the polarization of this wave. Also, you can do it with acoustic waves, and this is an ongoing project that in fact the people in the University of California is doing, and it's very close related with the thing that I'm going to talk today. So we are interested in this kind of problems. So in fact, when you look at this problem, in fact, there are many different known manifestations of the geometrical phases, which some are topological and some are not, and some are adiabatic and some are not. So for example, there are the Aharonov bond, which was one of the first, also the anions, which Professor Eduardo Franklin was one of the people that is starting with these ideas. But we are going to, of all these lists, we're going to focus on this Aharonov and anion. Why? Because it's known in many, in general, in quantum mechanics, of course, but the parameter space is, in general, can be in real or in momentum space, but you don't require the adiabatic condition. So this is a kind of generalization of the Berry phase, okay? So we are going to see how we can take advantage of this to look at the topological properties. So the idea is the following, is again, we will consider that we have some potential, we perturb the system in such a way that we move the parameters, in this particular case the momentum, and we are going to do it in a periodic way using having a certain periodicity on time, okay? So the idea is simple. Instead of if you can prove that if the system is periodic, then the wave function will get a phase, okay? And this is going to be called, this is going to be the total phase. And the total phase is given by the dynamical phase and this part, whatever is not this yellow thing, is going to be here. And this thing is going to be called the Aharonov and anion phase, okay? So what is the idea of the thing that we are going to show? The idea is that, okay, you can solve this very easily because it's just solving the time-independent Schrödinger equation or Dirac equation. Then you solve exactly this quantity, solving the time-dependent equation, and therefore you will get this, okay? So you get this, and from that you can get. Just put in the other side of the equation, that's it, okay? And this is the thing that I'm going to show, how to do it in solid-state physics, and what you can learn from doing this instead of looking at the band structure, which is the thing that most of the people do. So of course, why the people don't do that? Because for that you need to do the time evolution and find, basically you need to solve this problem. You need to find the wave function as you have an initial value and you need to find this unitary evolution operator that is here. And this operator usually is very complicated to find, usually use perturbation theory, Feynman diagrams and that kind of things. And for this case of that we are talking about periodic system, what we want is to find evolution after one period. So we want to find evolution, you take the wave function, and we want the wave function after one period of the perturbation potential, and so we want evolution. And in fact, you can always write this evolution operator as in this way, where you have here something that is called the effective Hamiltonian. So this is like taking stroboscopic photographs of the system after one period, okay? And whatever phase whatever evolution you get, you can put it in this shape, and this is the effective Hamiltonian. So what we want to do is find the effective Hamiltonian or find the exact shape of the evolution operator, okay? To find the adiabatic phases. And fortunately, we were able to do it in many cases, for example, in these biomaterials and graphene and so on. Basically, you start with the Hamiltonian, Dirac Hamiltonian, which is a two-dimensional matrix. So for example, you can shine light in graphene. So if you shine light in graphene, you will get this Dirac Hamiltonian, which is a 2x2 matrix when you have this vectorial potential of the electromagnetic wave. So the usual approach to solve this, because from this you can get also for example, the transmittance and the conductance and muonic properties of graphene that are really observed experimentally. But the thing is that people usually use perturbation theory. But perturbation theory has its drawbacks. First of all, it doesn't follow the Floquet theory, the Floquet theorem. The Floquet theorem says that if you have some Hamiltonian, and these Hamiltonians, for example, in this case, is time periodic, that means that your wave function needs to have this shape. So this is the equivalent of the Bloch theorem. The Bloch theorem is just a particular case of the Floquet theorem, but the Bloch theorem is applied in real space for periodic systems. but this is a system that is periodic in time. So it's the same idea. The idea is that your wave function is a plane wave multiplied by something that has the periodicity of in time. And this factor that is here is the quasi-energy, okay? Moreover, in two-dimensional, so what the thing is that perturbation theory is not valid for a strong field, because perturbation is always limited for very weak field. And also, the solutions of perturbation theory do not have the field periodicity, so you will never get the proper time evolution unitary, the time evolution operator, sorry, because it violates the Floquet theorem. And in fact, in material, in real materials, what you get is you have a space-time periodicity, because the wave, it's periodic in time, but also in real space. So what we did is that consider that the potential is a function of this thing that is the phase of the wave, okay? So knowing that, you can build the solution, exact solution of this kind of time-dependent problems. So in this case, our approach, we started with this problem, which was made right after the discovery of graphene, that you start with the Dirac equation, for example, like this, and you put a vectorial potential that represents the light, and this is given by the electric field, and here you have this phase of the wave, so you need to solve this equation. Okay, so what we did is to write the wave. So basically, we go in the time frame of the wave, and that means that you propose a solution that depends on the phase of the external wave that you are applying. So basically, what we did to solve the case of graphene with an electromagnetic wave is to propose a solution that is, again, in the spirit of the Floquet theorem, is something that depends on the phase of the external wave, which is a plane wave, and then something that is an spinor. And after a series of transformations that are here, this is not very important, just you need some transformations. Eventually, you transform this spinor into another spinor, and the thing is that this spinor, these are completely decoupled. So basically, you end up that the solution of this problem of graphene with electromagnetic wave that it was very complicated. It turns out that the solution is given by this Mathieu equation. The Mathieu equation, if you forget about this term, you will see immediately that this is the equation of a classical harmonic oscillator with a certain frequency. So this is the square of the frequency. Okay. So in this case, for example, you have a pendulum. This is a very famous example of this equation, which is in Santiago de Compostela, that all the people always put in this kind of. So you have the natural frequency of the pendulum, and then you drive it parametrically with certain frequency, okay? So here you have two parameters, the natural frequency of the pendulum, and here you have the driving, okay? And the driving, you can make a stability charge in the sense that, for example, if these guys, they drive the pendulum with a frequency that is the same or an integer of the natural frequency of the pendulum, the system will get energy and you will not get periodic solution, okay? Because this thing is going to be, so this is encoded in this chart that in this you have some regions that are forbidden, okay? And this is a very well-known example of resonance, so very simple stuff of physics textbooks. So basically, from there you get, for example, that you will open a gap and that kind of thing. So now, how is it related with, in this case, you can generalize this to other systems. For example, we did it for borofin and black phosphorus. When you have a Dirac Hamiltonian, but it is anisotropic, here you have different velocities of the electrons in different directions. And also you can tilt the cone. So this is like a generalized Hamiltonian. And you can, for example, try different kind of lights, linear polarizer or circular polarizer, solve the equation in this way, and you will get the quasi-energies. Well, the solution, again, let me show in this particular case how it happens. Again, you take your spinor, you apply a series of transformation, and you end up having this equation that is the one that solves the problem. So this is the solution of this simple, ordinary, second degree ordinary differential equation is the solution to this quantum problem. And you can see that there's appear very nicely a parameter here, which is the ratio between two characteristic energies of the system, the electric field induced by model and the photon energy. So in fact, it turns out that the solution of this problem already gives you what does it mean the adiabatic condition here, okay? When this parameter, when you are looking for a state that this is bigger than 1, you are looking for adiabatic states, and if Q0 is less than 1, you are looking for non-adiabatic states, okay? And this depends on combination of the velocity of the electron, the electric field, and the frequency of the external probe. And that gives you a precise meaning to the condition of adiabaticity. If this condition is met, then you can talk about adiabaticity and you do the usual stuff. If not, you need to do other things, okay? And this is again very similar to the Whittaker-Hill equation is like the Matthew equation, but it contains two frequencies, okay? It's like a pendulum with two driving frequencies, which are different. So how much time do I have? I don't know. I forget. 5 minutes. 5, oh, terrible. So thanks. Okay, so basically if you look at the quasi-energy spectrum, you get this. You see that here, inside here, you're in the region of non-adiabaticity, and outside you have adiabatic conditions. And for some fields, you can directly prove, for example, that for the adiabatic condition, it coincides with the very phases, but if we can calculate then the phases, so I will finish with this. Basically, for example, when you have weak field, which you can treat it adiabatic with circular polarization, this is the very phase, you see that you get this dot, which is related with the fact that the very curvature is concentrated at the Dirac cone. But if you look at the way that we are doing, using the Aharonov-Anandan phase, you get the same thing, the same phases, but around them you see these rings, and these rings are related with transitions, induced transition. That means that the Aharonov-Anandan phase not only contains the very case, but also shows you where you have the transitions, and also gives you the criterion to distinguish when you have a weak and a strong field. So for example, this is for the weak field linear polarization. The very phase is always trivial, but the Aharonov-Anandan phase is not trivial. It's only trivial in the x direction, with the applied field is in the direction of the momentum of the electron. And you can understand this from an analytical solution, by the way, okay? Now, if you apply the strong field with the linear polarization, you get this figure, which is very nice. The Aharonov-Anandan, you can see that, for example, again, in the x direction, the topological, it's topologically trivial, and the reason is because when you have your field in the direction, your electron field is in the direction of the momentum, there is no way of absorbing or photons because due to this conservation of angular momentum. But you get these rings, and these rings are the transition, and you get these pairs. These pairs, we don't understand what it is the reason why we cannot publish yet, okay? But we hope that maybe after this workshop, somebody will explain us what does it mean, but it's very nice. So there are, okay, this is the case of a strong field again. You see that you have a non-trivial region concentrated around the Dirac cone, but you get all these rings that are related with multi-photon absorbance, okay, with transition. So one ring, the first ring, you absorb 1 photon, second ring, 2 photons, third ring, 3 photons, and so on. So you get these transitions, so you get the topology, right? You get the condition, and you get these. And I think I will finish because I don't have time, no? No time, okay. So, okay. So in conclusions is that the time-driven approach in two-dimensional materials allows to investigate topological phases without the restriction or doing something strange things to you're really taking into account the adiabatic condition, and it will tell you when you have and when you don't have the adiabatic conditions. And this allows also to pave ways to quantum control, which there's a lot of interest in these kind of things. And especially, there are a lot of open questions that I know that some people, Eduardo and Luis, Foa Torres, are working on. What are the associated physical properties of these topological phases when you look at time-driven system? Okay, so I hope that you got more or less a clear view of what's going on here. Okay, thank you very much.
Okay, we thank Gerardo then, and we have time for some questions.
So in the case where the gap goes to 0, you get formally pair creation, like the example that I showed.
You get?
You get pair creation. When you apply your electromagnetic field, you produce particle-Hall pairs at the graphene points, essentially, at the K and K prime points, if you wish. That's because there is no gap. And so then you have then you have all this issue of the anomalies, the fact that there are formally two currents there too, and only one is conserved. So I think that's the analysis one needs to do in that case when there is no gap. Okay, so the adiabatic theorem there fails. Okay.
What?
There is no adiabatic theorem in that case. Okay.
Yeah, exactly. That's what we're saying, that there's no adiabatic.
In that limit, you cannot do it. Okay. If there is a gap, you can. Okay.
Yeah, but the thing is that, exactly. That's why what we are saying, that we are using time-dependent theory just because you don't have a gap.
Yeah.
And the thing that happened is that when you apply the light, it turns out that around the Dirac cone, you see this ellipse, which is not.
Yes.
This ellipse, this ellipse that we call it the balloon, is where you cannot apply the adiabatic theory. In the other regions, you can apply it, but not inside. But I don't understand the question.
But no, what I'm saying is that there should be an interpretation in terms of pair creation. Because you are creating particle-Hall pairs.
Yeah, I agree, yeah. Because the thing that the electromagnetic field, it's like open like a gap locally, yeah. And it's true that there are currents, because we know that.
It's a very simple clarification question. If you are deriving the system with external electric field, periodic electric field, my understanding is you would be depositing the energy into the system, but in the end, it seems that the system is not really changing the energy. Is there dissipation somewhere hidden that I missed?
No, there is no dissipation. You are putting energy, but this energy is like you put in periodically, okay? That's why when you get all these replicas, it's like you have the equivalent of the brilliant sunburn in time. Okay, so basically you are absorbing 1 photon, 2 photons, okay?
Well, if you absorb the photon, you deposit the energy.
Yeah, but but you will, it's like the brilliant thumb, you will like take modulus, okay? You know how much you put it inside.
You can also take it out of the system.
But that's the thing, they're not taking it out.
No, they are. There's coherent processes of depositing photons and removing them.
Is that the case?
Well, we are not having, I mean, when you put this A, I don't know if we are removing.
You have a Hamiltonian.
You have a quasi-Hamiltonian.
Yeah, you have a time-dependent Hamiltonian.
So the fact that you also emit it back.
Mm-hmm.
Otherwise, it would not make sense.
Mm-hmm.
Well, I mean, you can discuss this with more detail maybe here.
So I have, thanks for the very nice talk. I got curious. In one of your very last slides, there was this ring where you had the different colors and with circular polarization.
This one? Or?
No, one farther, closer to the end, I think. Yeah, that one. Question, how does this depend on the truncation? How does it evolve as you I think you expand the number of photons that you have in your space.
The thing is that just change is like a escalation of the radius.
Okay. Okay.
Because the photons here are the driving frequency.
Mm-hmm. Mm-hmm.
So basically, if you look at, it's just a scaling of the things. If you look at the parameters in the equation, original equation, you see that you get the frequency here. So basically what you are doing is just rescaling.
Mm-hmm.
So the rings, they move, you push them outside, and the size of the non-adiabatic region grows as you increase the field.
Okay, and the convergence with the number of photons you have in your space?
Our?
In the space you have, because I think you should be solving probably with a given number of photons in your variation space, or is
photons are given, you just solve this equation.
Okay. Okay.
In many cases, you get analytical solutions.
Okay.
So for example, for the Matthew equations, in fact, I didn't have time to talk about that, but in fact, it's very nice because if you are in the adiabatic region, you kill one of the frequency and you get the Matthew equation. And the Matthew equation, you can, if you plot, for example, the imaginary part. Here you have the imaginary part. The imaginary part and the real part of the spinor, the topological phases, which are adiabatic but topological, you get this precession of the orbit. This is precisely, you get this precession because you have this component in the Higher and the other band.
I see.
Yeah. So, but you never need to do that. You just solve this very simple equation.
Okay, one last question, Babak.
Thank you. So I just wanted to clarify, in your calculation of, I don't know if Anandan phase, you actually solve the full time-dependent problem, right? So you find the Floquet modes and so on.
Yeah.
And then from those, you're calculating the phase.
Yeah, you solve that, and you also solve the instantaneous eigenvalues. So you get...
Yeah, okay, so that's the part I don't quite understand. So you're applying adiabatic theorem to solve, to calculate it? Because that n of r is not necessarily as a solution for the Schrodinger equation.
What?
That n of r there would not be a solution to the Schrodinger equation.
This?
No, the ket n-r in that expression.
No, this is not, okay, you solve this you can always get it by solving the time independent.
Yes, you can, but it's not the solution for
No,
Schrodinger
it's not
equation.
the solution. You get the solution from the whole equation here. Okay? You get this by solving this equation that I show you.
Yeah, but the two would not be equal.
No, you have this, and precisely.
No, the kets are not equal. The phase is a different thing. The vectors are not equal. Up to a phase.
You mean this?
Yeah.
Oh, no, yeah, you understand well.
Okay, so you solve the left side. Is that what you're doing? You solve on the left the phi.
We solve the left and we solve the right, and with some transformations, yeah.
Okay, so maybe I'll talk to you later.
I can do I think this n ket is just the eigenvalue equation for the Hamiltonian.
But phi is supposed to solve the Schrodinger equation.
Yes.
And the two will not be equal up to a phase.
Well, let's thank Gerardo again. And,
Well,
and
let's go. Okay.
and now we can go to the coffee break, before starting the next session.